Hi, my name is Louis. Welcome to the Standard Pro Training Power Hour on 3-wire and 4-wire ignition coils. What we're going to be covering here are what do those 3 wires and those 4 wires at the ignition coil actually do. Typically, when we look at the 3 wires or the 4-wire coils and we see the heavier gauge wires, we know that's power and ground. We need to look it up in service information to verify. Where the difficulty comes in sometimes is what are the small wires, especially when you got 2 small wires or 1 small wire. And why do they run 2 grounds? Why do they run an ignition feedback circuit on some of these coils? That's what we're going to be covering in this Standard Pro Training Power Hour. With that said, let's get started. As we mentioned, we're going to be covering 3 and 4-wire ignition coils. What we're mainly going to focus on are the small wires. The small wires are always the tougher wires to diagnose. When you see the heavier gauge wires at an ignition coil, you typically know that it's going to be for power and ground circuits. Always got a reference to a wiring diagram to make sure what we're testing actually on the vehicle, but the small wires have always been the discomfort. Now, typically those small wires are pretty conventional and do the same thing from one manufacturer to the other, but there are going to be some differences when we cover these coils. When we cover the 4-wire coils, that's where you start seeing some significant differences from certain manufacturers of what they're doing with the small wires. The big wires, the heavier gauge wires, they're going to kind of stay the same. That's going to be some type of power or ground supply like it's always been. So let's go to the PowerPoint presentation and let's start talking about these 3 and 4-wire ignition coils. What we're going to do is provide you with how they work, more importantly, how to test and provide some power tips along the way, especially on how to avoid repeat ignition coil failures. First thing that we're going to do is just a quick review on how ignition coil works. But we still have to do, whether it's a 3-wire, 2-wire, 4-wire coil, we still got to end up at this place right here, where we got to take the primary winding, energize it with power and ground, turn it off, and then collapse that primary into the secondary and get spark to the spark plug itself. And then we're going to repeat that cycle. In order for the ignition event to occur correctly, there are some basic timing controls that are being done in crank mode to get the car started. As you can see, the big ones here are RPM and cam position. But you also see that we have labeled the map sensor as an input. We all know that some cars don't have map sensors. This is why I have put our first power tip in there, the barrel sensor. The barrel sensor is going to be a primary input into the module that's controlling spark timing on the vehicle, engine control. And that's why I highlighted it here in the importance of the barrel sensor. If the barrel sensor is out of calibration, it will affect ignition timing on this vehicle or can cause erratic spark on the vehicle. Once the car is running, a bunch of other inputs are going to come into place here. That's when the module is now going to, and we don't have all of them here, but that's when the module is going to provide additional control of the timing and move away from a basic ignition timing to an enhanced ignition timing control. That's where it's going to have the ability to retard, advance the timing based on the conditions that you see up on the screen here. An example would be intake air, coolant temp, atmospheric pressure correction, knock control. That's a reminder. That could also be a power tip that we have to pay attention very closely to see if there's any knock correction occurring on the vehicle. And then eventually we end up at whatever desired timing the module wants it to be at. What it comes down to is that they're trying to create maximum pressure, which is going to equate to maximum power at the correct time. This is why the timing is controlled before or after top dead center, depending on the application. Most of the time we're going to be at before top dead center. But the idea here is to create the maximum pressure 10 to 30 degrees after top dead center, when the piston already has started coming down, to create spark and create that maximum pressure to create the maximum power. And obviously that's going to turn into the rotation of the crankshaft. Why do we end up here on whether it's 2, 3, 4-wire coils? We're concentrating our effort here today on 3 and 4-wire coils. We have a spark check on the vehicle that is done correctly. I'll expand on that in here in a second, and it fails. An example of checking for spark correctly would be this ST125, which provides a load of about 25 to 28,000 kV or kilovolts in order for it to jump the gap on this tester. Some of you guys like to use the expandable testers where you can take it out to 35, 40 kV and look at the spark that way. What you don't want to do is use a spark plug outside the cylinder, ground the housing of that spark plug and see if it has spark. Because that's only going to take maybe 2, 3, 4 kV to jump the gap on that plug outside the cylinder. So this is a typical 3-wire coil. And this is what you usually end up with. Always reference the service information, but this is very repeatable on domestic Asian and European cars, that if it's a 3-wire coil, this is most likely what you're going to have. Where you're going to have a power supply that we have to test. You're going to have a ground supply that we have to test. And then the smaller wire, the trigger wire from the module to the coil, is where we're going to focus most of our attention with this power hour presentation. In this example, which just happens to be a VW Audi, but it's pretty typical on other manufacturers too, where you have a battery voltage power supply, you have a ground, another ground, and then the trigger from the PCM for the coil. Now you notice that on this example here, there are 2 grounds. And if you look at the picture, you can see very clearly that there is a significant difference in gauge size between those 2 ground circuits to the coil. More on that, as we go. I want to take you over to the bench momentarily to start IDing some of these coils. So here goes an example of a 3-wire coil on here. So I'm going to try to turn this so you can get a pretty good, there you go. You can see the 3 terminals on that 3-wire coil, which is what we just talked about on the picture that I showed you, very conventional. This is another example over here of another 3-wire coil with the 3 terminals, which are typically going to be power, ground, and the controller trigger to the ignition coil. Let's go back over to the presentation. And what I'm going to do now is take you through a broken car, a vehicle that has a problem with a 3-wire coil. The first manufacturer that we're going to talk about here is Nissan itself. If you look at the diagram, you could see that it is a typical display of what I previously showed you with the power and ground and the control from the module. The vehicle that we have has misfires and ignition coils have been replaced twice. All of the ignition coils have been replaced twice. This 2015 Nissan with a 1.6 has repeat coil failure. And obviously that's one of our objectives here. How do we avoid that from happening? In typical Nissan Infiniti fashion, we have a 300 code multiple cylinder misfire on the vehicle. Nissans are not the best at IDing the actual cylinder, either with the code or with scan data. So an example here, which many of you have joined us in our Mode 6 classes before, in this example, we're using Mode 6 to hopefully narrow down what cylinder is causing the problem. In Mode 6, even though this is not the complete picture and we don't put all our eggs in this basket, Mode 6 is indicating that right now, the most problem child appears to be number 3 cylinder. We start our diagnostic testing with a lab scope, and we're going to look at amperage for all 4 ignition coils. And because Mode 6 ID'd a potential problem more significant in 3 than the other cylinders, we're going to attach the voltage leads of our lab scope to coil number 3. We have our ground connection directly to the ground that goes to the ignition coil, and then the trigger on the other lead from the ECM to the ignition coil itself. As soon as we look at this pattern, we can see that the trigger is there. As we progress, we'll discuss this a little bit more, but for now, I want to focus in, and I'm going to do a little zoom here. And I want you to notice the approximate voltage on that trigger circuit is about 5 volts on the turn on from the ECM to coil number 3. It will not always be the same level for the trigger circuit on all manufacturers. We have to have an understanding that they're not all the same. For this example, we're about 5 volts. Right away, we can see by looking at the amperage of all 4 coils that the trigger is there, but there is no current flow through coil number 3. Even though we're not showing the triggering events for the other coils, we can see that the other coils are flowing current, and the amperage on these is going up to about approximately, I'm going to just do a quick zoom in there for you on this here, and we're probably going to maybe about 11, 12 amps on the coil. So the decision is made, let's put number 3 coil in on this car. And after a while, it's unpredictable, the time frame here. May take a couple days, may take a week, the repeat failure occurs again. Which is kind of bringing us to our first power tip, or our second power tip in this power hour, is that this coil is showing signs of it being the actual molded plastic housing being melted. So when we have this event occurring on ignition coils, which obviously is not isolated to just Nissans, we have seen this on other manufacturers, we start thinking, what could be the problem with these ignition coils? Could it be bad grounds? We put that at the top of the list because many of you are aware that bad grounds are the #1 cause of this. But we do have some other possibilities. High secondary resistance, the coil has to work twice as hard as it would normally would as far as outputting kV, voltage. And we could have a driver inside the PCM that is holding that coil turned on for an improper extended period of time. The ones that are unlikely but have to be at least mentioned are the fuel mixtures themselves, especially specific to that cylinder if I got a weak injector, or anything that can cause that coil to work harder. This one happens to be a loose ground by the alternator housing. That ground is loose. You can grab it with your hand and move it. It's not tight. Once that ground is tightened up, 4 new coils are put in, because now those 3 coils plus the new one that's the 3rd time around has failed, and these other coils are unpredictable how long they're going to last, even though they've been changed a couple times. If we take a look at the Ford 3-wire coil, it is very conventional as far as the amount of power and ground that's going to be supplied to that coil. It's what we're very used to on other ignition coils. And then you have the trigger circuit coming from the module to the coil. Ford 3-wire coils are not brand new, but newer compared to how long they used the 2-wire coils. They also, when the 3-wire coil showed up, they also started using index spark plugs. And I need to rephrase that a little bit better. It doesn't mean that if it has a 3-wire coil on a Ford that it automatically is going to have index spark plugs. They didn't start using them to about 2021, 2022, right in that time frame there. So it's a few years they've been using them. But it does have to be mentioned here as a little power tip that make sure that if this vehicle, a Ford, and other manufacturers do index spark plug also, but on a Ford, if it has supposed to have index spark plugs, that we put index spark plugs in there. We're trying to avoid some type of an additional failure, a repeat, a comeback, or a drivability problem that can be very difficult to diagnose. You could end up with something as a straight misfire or some type of a misfire only under heavy load while you're driving the vehicle down the road. To take a look at how this coil is triggered, to expand on that, we could see that we are using a secondary paddle. Let me take you over to the bench here for a second. So we're using the picoscope to do the analysis on this vehicle. And this is the secondary paddle that's being used with the picoscope simultaneously to look at the pattern that we're looking at right now. So we're looking at amperage, we're looking at the secondary through a paddle, and then we're using the picoscope to look at the trigger circuit at the same time. Let's go back. So first of all, what I want to start with is I'm going to go from the bottom up. That is the secondary kV using that paddle. And it gives us an indication here that there is a secondary event occurring. If I move up, you could see that the secondary event is also matched to the trigger on this car. So what you see is if you go from, on the second line, go from left to right, you can see the trigger circuit. I'll back up just for a second just to make it clear. You can see the trigger circuit from the PCM to the coil. And on that trigger circuit, if you look closely, it is happening twice. So this is what Ford and other manufacturers done, but Ford is probably the most recognized one, where they're using multi-strike event on this vehicle. So on the first trigger, you could see that the voltage is expanded there for a little longer period of time. It's turned off and then turned back on. This appears to be slow motion, but this is happening very quickly. So this piston is coming up on the compression stroke. We're trying to dial in the ignition timing perfectly on this vehicle, but they are using multi-strike to do that. Other manufacturers do that. My point here is that if you see this event, if you're a scope user, many of you have been exposed to this throughout the years. If you see this event and it's not what you normally see on other vehicles, as far as the multi-strike is concerned, it is a normal occurrence. Not just Ford, just a friendly reminder here, make sure that you look at bulletins. In this example here on this 2015, 2018 Ford Focus, if you retrieve codes in this vehicle, and you can see the codes up top of 300 or 316, what they're telling you is to either re-gap the plugs that are in there or install new plugs, but more importantly, reprogram the PCM. Sometimes that's the only way out. A lot of the times these are the cars that turn on the light, but don't exhibit a physical misfire that we could feel in the car. Moving on over to 4-wire coil. And we're going to use Toyota as our example because it kind of is different as far as the typical layout of the 4-wire coil. So what you have, if we just do a quick run through here right now, you have power, you have ground that is being shared by the 4 coils. I want you to take a look at what they call IGT, IGT2, IGT3, and IGT4. Those are the individual triggers for the coil. What's a little bit odd here, if you don't work on these cars, is the IGF circuit. On the 4-wire Toyota coil, instead of having 2 grounds, which is what you typically have on almost everything else, you have this IGF circuit that is common to all 4 coils. The IGF circuit is spliced to all 4 coils, and you're going to see what happens here on the next slide, what the IGF does every time a coil gets triggered. So let's explain that with a lab scope pattern. So pick any coil, doesn't matter. This is a typical event on any one of these ignition coils. So let's start with the middle one, the IGT, which is the ignition trigger. And if you come back here, apologize. IGT is the trigger from the module to the ignition coil. So there goes the turn on circuit. And on this one, if you look, it is going up to about 3.6 volts. That's why I said they're not all the same. That's usually a loading effect of the ignition coil itself on the trigger circuit. A lot of times if you do this test open circuit, and you got to be careful because the module may shut down because it sees an open circuit, you will usually see that go up to 4.5 to 5 volts. But connected is the proper way to do it, and we're loading it down with the coil slightly, and that's why it's going down to 3.6. At the same time, we got our amp clamp connected, and we're seeing that the amperage is, on this example, is jumping up to, a little bit over 10 amps, maybe hitting about 10.5 amps there. So we could see the turn on, the amperage increasing in the coil primary, and then we could see the turn off, and you could see the amperage instantly go to 0. So that's very conventional compared to other vehicles. What's a little bit different is the IGF. The IGF is getting pulled from 5 volts. It starts out at 5 volts on the left hand of your screen. When the IGT to any coil gets turned on, like we see here, the IGF circuit will get pulled low. You can see there's almost a delay in when the IGF went from 5 to 0 volts, which is the 3rd line on the screen. What's happening here is that once the coil current gets to a specific amperage, which is about 2 to 3 amps, that's when the IGF will pull the 5 volt line. That's when the IGF will get pulled from 5 volts to 0 when the coil current reaches a certain level, which is about 2 to 3 amps. That's why you see the delay between the trigger and the IGF going from 5 to 0. Let's apply this information to a broken car. We have this 06 Scion with a 1.5. The condition on the vehicle, it starts, runs for a couple seconds, and stalls out. We hook up a scan tool, and we have P0351, coil A primary, 352 coil B, and 354 coil D. So we got basically electrical codes for 3 out of the 4 coils. The connection. We're going to check amperage to all 4 coils simultaneously. Now we're going to look at IGT for coil number 1, and the IGF circuit, which is common to all 4. And you can see we're using the ground circuit that's being provided to the coil for our lap scope connection. A little terminology here. That IGF has been called basically 2 things since the beginning of time. It's either called ignition feedback or ignition failure, depending on what literature, diagram, flow chart you're looking at. And IGT has been called ignition trigger or ignition timing. The kind of the official terminology is really ignition failure and ignition timing, but it's been called feedback and trigger forever out in the field. Either way, it's the same circuit. Let's see what we have on this one. We're looking at the trigger for number 1. So we do have a trigger, the top line for number 1. If you look at the voltage on that one, it's about 4 volts on the trigger circuit. So we do have trigger to number 1 coil. The reason we're here, one of the codes was for coil number 1. We just picked number 1 to start with here. We also have current flow for number 1. All you gotta do is follow it straight down, and you can see it lines up with coil number 1. We're getting current flow on this one at about approximately 11 amps. We also have an IGF for number 1, and you can see the delay there on the IGF, for number 1. What is not good here is that we have the IGF stuck low at 0 volts when it should be going up and down. It should be starting at 5 volts and then dropping down to 0 as we trigger these coils here. And if you look, the other coils are being turned on and off. We don't see the IGT because we're only looking at IGT for number 1, but the IGF being at 0 volts when it's not supposed to be, that is the problem child. That's why we're getting all those codes. The IGF is the feedback to the module to let it know, hey, you sent out a trigger, and now I'm sending the signal back to you, hey, that this coil has been triggered. And in this example here, it is stuck, most of the time stuck at 0 volts. We disconnect coil number 1, unplug it. We now go to coil number 2 and start triggering off of coil number 2. And now we have a normal IGF circuit where it's at 5 volts and only dropping to 0 volts when each coil is getting turned on and off. Obviously, number 1 is out of the loop right now, but 2, 3, and 4 are in the loop, and now we have a normal IGF circuit. With 4 new coils in there, we now have conventional IGF, coil current, and IGT, where now the IGF circuit is at 5 volts, and the only time it drops down to 0 is when an ignition coil gets triggered, and when that coil reaches a certain amount of amperage, the 5 volts gets pulled to 0. The small events that you see in between the ignition coils, it just happens to be the power supply to the injectors, and that's why you're seeing them, on our pattern. Somewhere along the line, Toyota went to 3-wire coils. They have a few years here also, so now they have joined kind of the rest of the world here in the conventional operation. They got rid of the IGF, and now they have power, ground, and IGT. And that is as conventional as it gets, where you have the IGT and you got the typical coil current. These are jumping up to about 12 amps or so. And we have a conventional IGT here at about maybe 4.5 volts on this one. That's why you see the design changes will change the amplitude of the IGT circuit, not just from the module, but also mainly from the loading of the ignition coil onto the IGT circuit. And then the low amperage that you see there at about 1 amp or so, that is from the injectors themselves. We move on over to GM 4-wire coil. We get an opportunity to talk about 4-wire coils. If you look at this one here, we have power. We have a power ground, G113, and we also have what they call an ignition ground coming from the module. It can be comparable to a sensor ground. When we're talking about coolant sensor, map sensors, we have a sensor ground coming from the module itself. The reason they do that is to reference the trigger circuit off a ground from the module. It's basically for the trigger circuit itself. If we look at the amperage and the trigger, pretty conventional, where the amperage is going up to about 9 amps, and the trigger circuit is running a little bit over 4 volts. You're about maybe 4.2, 4.3. But outside the conventional power and ground, this is the trigger circuit to the ignition coil. So you can see it follows suit of the other ones. We look at this 2012 Impala 3.6. It basically has a no spark condition. We pull up the wiring diagram like we're supposed to. Now we're going to do something a little differently here, because now we're going to use 2 channels of the lab scope. One channel, A, is connected to the power and ground supply. And then channel B is connected to the control side from the module, and the ignition ground, or sometimes typically a lot of GMs will call it the low reference ground, from the module to the ignition coil. So there are 2 measurements that are being done here. If you look at the pattern up on the screen, the channel B, the top one, is the trigger. And we're running here 2 volts per division, so we're pretty much hitting 5 volts there. At the same time, we're looking to see, hey, is my power and ground supply, which we haven't mentioned up till now, but it applies to everything that we discuss here, is my power and ground supply good to this ignition coil? We're using a scope, we're letting it run, we're letting it trigger, and we're looking to see if the power and ground. So that's what you see on channel A. We're referencing G113 as our ground, and we're looking at the power supply going to it. Nothing really stands out here as far as the power and ground is concerned to the ignition coil. But many times, right, we take shortcuts to see if we can resolve a problem quicker than maybe spending a bunch of time diagnosing on it. Putting an additional ground to G113, because G113 is the common ground for the coils, and all we're doing here is saying, you know what, we have seen this ground circuit cause a problem in the past, it's G113. Hey, why don't we just put a ground right to from a stud right to one of the coils and see if we fix the vehicle, and that takes care of the problem. So there's nothing wrong with, it's a power ground, chassis ground, supplying ground to it to see if it eliminates a problem. Some past experience kicks in here that, hey, this G113, we have seen problems in the past causing multiple issues, and this is one of them here. So there's nothing wrong with it, and that what fixes this vehicle. We end up going to G113, and we find a bad ground connection there and repair that. As a review, before I take you back over to the bench to take a look at some of these coils again, as a review for these ignition coils, on a typical control circuit on the left-hand side of your screen, the amplitude on that one, which I got highlighted here, is 4 volts. A typical control circuit, what you see on the right side, is about 5 volts. And it could be, as you saw here, some of our examples where we run from, we could be down to about 3.5 volts all the way up to 5 volts. And that has to do usually with the coil itself. Many times the control circuit or the trigger circuit, no matter what terminology they're going by, will typically open circuit go up to 5 volts. Cautious with that, but that's what typical. What usually causes the amplitude to go lower, which is nothing wrong with it, unless it's abnormally low or not getting pulled down at all, is the ignition coil design itself. Before I take you over to the bench itself, I want to talk about the additional resources, and then I'll take you over to the bench. There is our YouTube channel. On that YouTube channel, standardbrand.com, there are some very straight to the point, procedural, how to take something apart and put it back together, or diagnostics. Hey, this is what's wrong with the car, and this is the quick, short diagnostics to get to the problem on our YouTube. So this is a lot of technical references, our YouTube channel. If you go to standardbrand.com, you get an opportunity to also see some background or information on ignition coils at standardbrand.com. When you get an opportunity, go there. There is some technical background information on all our ignition coils at standardbrand.com. Before we close out, let me take you over to the bench for one additional power tip. When you are going to change these ignition coils, please inspect thoroughly the connector and the wiring to the ignition coils. Some manufacturers are prone to failure of the connectors where the back side starts to back out, or the front side, we lose terminal tension on the front side that connects to the ignition coil. So make sure to inspect these coils thoroughly and to inspect the connectors themselves for any damage that's going to cause additional failures down the road. And remember, even though we provided you a lot of information in a short period of time, you can always reference our two websites, the YouTube channel and standardbrand.com. Before we close out, Mr. Corey, are there any questions that we want to go through?
We actually did have a couple of good ones, Louis, and I answered a few here in the background, but I do want to address a couple because I know these are pretty common questions. One, and I know you talked about it a little bit throughout the class here, but just to clarify, why are there two ground wires on the 4-wire coils?
Okay, so the most common when it comes to 4-wire coils are power, 2 grounds, and the trigger, control. The reason that they have 2 grounds there is that we need the power ground for the primary side of the coil, and then the other ground, like I mentioned, is a sensor ground. So they want this filtered sensor ground from the module because they want the trigger circuit from the computer to the ignition coil itself to be off the regular ground, because at regular ground there's a lot of electrical noise there, and they're trying to keep that trigger circuit as clean as possible and avoid any interference from the regular high voltage ground, the 12 volt ground there, and keep it at the low reference. That's why GM typically calls it the low reference ground.
I think that answers that well. Here's another one, and I know I used to get this question a lot. What is the purpose of indexing spark plugs?
On the indexing spark plugs, we mentioned that on the Ford. Indexing spark plugs in automotive has been around probably longer than I've been around in automotive. It is not brand new, especially whoever does racing out there, you know, which I don't do any racing, but whoever does racing has been doing that for years and years on cars too. But on the Ford application, as an example, they want the electrode facing in a very specific direction inside the combustion chamber, which usually comes down to tailpipe emissions and fuel economy, trying to get the most out of the combustion event in that cylinder.
All right, I'm going to do one more here in the spirit of time, Louis. Why was it that the Toyota start and stall with one bad coil?
Okay, yeah, on the start and stall, the reason that was happening is that, and it felt like, and if you were in the vehicle on this car, it felt like you were in a theft, because it would start and run for a couple seconds and then stall out. And the reason that was happening is the module was turning off the injectors on there. When it did not see the proper IGF feedback on that IGF signal, it went into a strategy mode where it says, you know what, we're going to shut down the injectors on this vehicle. If I don't know what's going on with the ignition coils, I'm not going to let this car run because my timing events could be off and I don't want to create additional problems in the vehicle itself, damage to the cylinders or whatever it might be.
That makes perfectly good sense to me. Well, again, in the spirit of time, we're going to keep it at that. Louis, I'll thank you for being here. I want to thank everybody else for being here, and I'll let you close us out.
Again, provide a lot of information in a short period of time. Make sure you reference our YouTube and Standard Brand channels. Thank you again for being here with us. Until next time, have a good day.